When you're making those really critical decisions, maybe in manufacturing or complex testing, how much do you actually trust the measurements that are guiding you?
That's a great question. What if that super precise piece of equipment, starts telling you something that's just slightly off?
Exactly. Today, we're doing a deep dive into something that sounds technical, but is surprisingly fundamental. Load cell calibration. Our mission here is to unpack what calibration really is, why it's definitely not just a nice to have, but absolutely essential.
Yeah, it impacts everything. Product quality, safety, even regulatory stuff.
Right. And we've got some great material that really lays out just how indispensable this whole process is.
And, for anyone out there who relies on precise force measurements, getting the why behind it is, it's key.
Because it has real-world consequences, right? For your data, the decisions you make based on that data.
Absolutely. We're essentially talking about applied metrology. It sounds fancy, but it's the practical science of measurement.
Applied metrology.
Yeah.
Okay.
And calibration, at its heart, it's all about checking, verifying that you're getting accurate, traceable measurements from your gear consistently.
Okay, let's unpack that. When we're talking about something specific, like a load cell or maybe a torque transducer, what is calibration in that context? Is it just like a quick adjustment?
No, it's definitely more involved than just a quick tweak. Think of it as the science, really, of verifying that your instrument is accurate and traceable.
Traceable meaning? Traceable to what?
To a known standard. It's a core part of that applied metrology we mentioned, making sure your tools are, performing precisely as they should.
So how do you do that? How do you verify it?
Well, the process involves a pretty rigorous comparison. You take the sensor's output and compare it against a highly precise reference standard.
Like another even more accurate load cell.
Yeah.
Or certified weights.
Exactly. Could be a master load cell, could be precision weights. And based on that comparison, you make adjustments or at least document any deviation to ensure that sensor is performing within its specs. The source material really drives this home. If your load cell starts drifting, even subtly, or gives you inconsistent results, well, how can you trust the data?
Yeah, how do you make decisions then?
You can't, not reliably. And that's precisely why this verification, this calibration is so vital.
It really sounds like it's less about just making sure it works and more about having absolute confidence in those numbers. Which brings us nicely to why it's so critical. The sources highlighted 5 key reasons.
That's right, 5 indispensable reasons.
Let's dig into the first one, managing uncertainty.
Yes, number 1, managing uncertainty. Look, every single force measurement you take, it inherently has some level of uncertainty. You can't escape it.
Right.
Calibration ensures your device's measurements are traceable, usually back to the SI unit of force, the Newton, and it actively helps you keep the measurement uncertainty within whatever range you actually need for your application.
So you know how precise your measurement is, and if it's precise enough, makes sense. What's reason number 2?
Second, it ties directly to quality and spec performance. Basically ensuring the sensor meets its published performance ratings.
How it's supposed to perform.
Exactly. If it doesn't, that can directly mess with the quality of your testing or your manufacturing output. So calibration ensures it does meet those specs, which, reduces risk and ultimately saves cost.
Right, because if your sensor is off, your product might be out of tolerance or your test results are just wrong.
Precisely. Leads to waste, rework, all sorts of problems.
Which I guess ties into the next point, preventing problems before they happen.
You got it. Third is minimizing downtime. This is really about being proactive.
Instead of reactive.
Exactly. If you stick to a regular calibration schedule, you're much more likely to catch potential issues, little drifts or inconsistencies, before they become total failures.
So you avoid that sudden everything grinds to a halt moment.
Fewer unexpected stops in production, fewer delays in testing. It avoids those really costly interruptions.
Okay, that ounce of prevention idea makes total sense. Now, beyond just stopping outright failure, how does it affect the data itself over time?
Well, that's the 4th key reason. Supporting data accuracy. You have to remember, these are mechanical electrical devices.
Things wear out, drift.
Exactly. Load cells degrade over time. It's just physics. Use, environment, age. It all contributes. Calibration helps identify and correct common sources of error.
Like what kind of errors?
Things like zero offsets, where it reads a value even with no load applied, or nonlinearity, where its response isn't quite proportional across the full range. Or hysteresis.
Hysteresis, what's that?
That's when you get a slightly different reading applying a load versus removing that same load. Calibration catches and corrects these things, keeping your data reliable.
So it's like tuning up an instrument to make sure it's still playing the right notes accurately. Fighting that inevitable drift.
That's a good way to put it.
And the final point. This one's often a big deal in certain fields, right?
Oh, definitely. Number 5, regulatory compliance and certification.
The paperwork trail.
Well, it's more than that. In many regulated environments, think aerospace, medical, automotive calibration, isn't just, good practice. It's often a hard requirement for accreditation, for certification.
So if you want that stamp of approval, you need proof of calibration.
Absolutely. Auditors, quality managers, they specifically look for things like ISO IAC 17025 accreditation.
That's the big international standard for calibration labs.
Yes. And traceability to standards like those from NIST, the National Institute of Standards and Technology in the US. They need to see that unbroken chain of comparisons back to a recognized standard. Calibration provides that proof.
Okay, so for many users, it's just non-negotiable. You have to do it. Which makes sense, given the stakes.
Yeah.
It sounds like a pretty rigorous process then, not just a quick check. How does it actually work in practice?
It is, yeah, it's quite thorough. For example, when you get a new load cell from a reputable manufacturer, it almost always undergoes a full detailed calibration in their lab before it even ships.
What does that involve?
Usually tests for things like repeatability. Does it give the same reading every time for the same load? Linearity, is its response consistent across the range? Zero balance, things like that.
And you get proof.
Always. It comes with a traceability certificate detailing the results and the standards used.
Okay, that's for new ones. What about ongoing calibration or sensors from different companies?
Good point. Many places also offer third-party calibration services and repairs too. They can often handle sensors from various manufacturers, not just their own.
So you can send your existing equipment in.
Right. And some of these labs handle a huge volume. The source mentioned one provider doing over 100,000 calibrations a year. That tells you something about the demand.
Wow, that's a lot.
And for companies that want to handle it themselves, maybe they have a lot of sensors or very specific needs.
They can set up their own pellicle lab?
Essentially, yes. You can get specialized calibration-grade load cells, entire calibration systems, and even the software to manage the process in-house.
Interesting. So lots of options depending on your scale and needs. Now, this robust process, it leads to the practical question. How often? How often does this critical calibration need to happen? Is it just once a year?
Well, once a year is kind of the general rule of thumb you hear most often, but
Okay.
It's definitely not set in stone. It really depends heavily on how you're using the sensor.
Like if you're pushing it hard.
Exactly. If it's seeing extreme loads, maybe close to its capacity, or if it's operating in a really harsh environment, temperature swings, vibration, moisture.
Just used constantly, day in, day out.
Right. Heavy usage cycles, any of those things would probably mean you need to calibrate more frequently than once a year to maintain that accuracy, maybe every 6 months, maybe even more often in some critical cases.
Are there warning signs? Like how would you know if it needs it sooner?
Yeah, definitely keep an eye out for unexplained weirdness in your data, anomalies, or if you notice a consistent drift in the measurements over time. Those are pretty clear signs it's time for a checkup, for a recalibration.
Okay, that makes sense. Now you mentioned repairs earlier too. What's the actual difference between calibration and repair? They sound kind of similar.
They do, but they are distinct services. Think of it like this. Calibration verifies performance. It checks if the sensor is accurate within its specs and maybe involves minor tweaks to bring it back in line.
Like fine-tuning.
Sort of, yes. Repair, on the other hand, is about fixing something that's actually broken or damaged.
Like physical damage.
Could be physical damage, sure. Or it could be a faulty connector, a damaged cable, maybe something wrong with the internal electronics, the strain gauges themselves. It's about fixing a component failure.
So how do you know which one you need? If your data looks funny, is it calibration or repair?
Good question. Generally, if you're seeing that slow, consistent, gradual drift we talked about, the output is off, but it's still kind of predictable. That usually points towards needing calibration.
Yeah.
But if you suddenly see wild, erratic jumps in the readings, or the output drops to zero, or it's just completely unstable, that's more likely a sign something is actually damaged and needs repair.
And obvious physical damage, like a bent connector or cut cable.
Oh yeah, that's definitely a repair job. And usually with repairs, the process involves a full inspection first. They'll figure out what's wrong and give you a quote before they actually fix anything.
Right, so you know what you're getting into.
Exactly.
This whole deep dive,
Yeah.
it really makes it crystal clear just how foundational calibration is. It's not just some technical detail.
Not at all.
So boiling it all down, what's the main takeaway for everyone listening?
I think the core message is pretty straightforward. Doing regular calibration, it really protects your investment in that often expensive equipment. Critically, it keeps your data accurate and trustworthy.
Which you need for making good decisions.
Absolutely. And it helps you meet those vital quality and safety standards, not to mention any regulatory hurdles you might face.
And there's support available.
Oh, yeah. Most reputable calibration providers have support teams ready to help you schedule things, track your equipment with RMAs, even set up custom service packages if you have unique needs. They often keep your calibration history on file too.
Which must be handy for audits.
Incredibly handy, makes documentation so much easier.
Okay, so this conversation really underscores that trust in your data, it fundamentally starts with precise verification, with calibration. Which leaves me with a thought. If accurate measurements depend on proper calibration, what other areas, maybe in your work, maybe even just in life, rely on some kind of foundational calibration that you might be overlooking?
That's an interesting way to frame it. What needs its own checkup?
Exactly. Maybe it's a good time for everyone listening to think, are my sensors or my equivalent systems due for their own verification?